Ladies and gentlemen, Mr. Chairman, dear organizers, thank you very much for you all being here. Thank you very much for me having a chance being here. And up front to my presentation, please allow me one comment. I think I spent a good part of my life in clean technology, clean energy, particular zero waste products, etc., etc. But I like to comment on one of my forehand speakers, and I like to tell you my understanding, and I want to tell you that the Intergovernmental Panel on Climate Change, for my understanding, is not a fact. For my understanding, it's a religion that asks you to believe. And this I want to say at the beginning. So the topic of this presentation here is nanostructures for zero-emission future transportation, energy and economy. We don't have too much time, so some of these pictures I'm going to show you, I will just fly over, and after that I would just ask you, we have enough time in the evening, and then you may ask me for further comments on that, including the IPCC, of course. So I'm going to actually hit here. This doesn't work? No. I'm going to hit 4 topics: tantalum, which is a super lightweight material made by controlling grain size by nanostructure. If there's anybody in this room who is feeling very strong, he might come to the front right now and try to bend it. I would appreciate that very much. The second topic here is a public bridge. That is the public bridge number 1, has been set up in November, and this is an expression for a high-performance Portland cement with an enormous potential of CO2 emission saving. Number 3 is the H2 on Air project, which is actually representing here not an innovative, but a successful way of hydrogen storage for future transportation and all our energy-related concerns, and that results actually in something that is called power to gas to fuel. Power to gas, everybody's talking about that, does not have a chance to have a foot on economic floor today. Power to gas to fuel could. And actually this is the one that we are nominated for the German Environmental Award this year. Now, that was actually very recently, a few months ago in Dublin, and I want to draw your attention actually on the picture on the very right in the bottom. This is the so-called Euro Nano Award. We didn't win it, but we made it. And the Euro Nano Award actually contains 17 bars of tantalum. This is the super lightweight material, and this is embedded in high-performance cement. And that was handed over, that was in Dublin in June this year. Now, to the tantalum that is what we call lighter than aluminium, as strong as steel. It's an aluminium matrix material where we are controlling grain size by adding in a nanoscale nano tubes, carbon nanotubes. That will be the first topic. The second one, this is the high-performance cement, and what you see here on the top picture on the left, this is the bridge that was built in Germany in November last year. On the bottom, this is the plant that we utilize to manufacture these materials, etc., etc. The interesting thing is this is a BMBF project. Since I will show you that since 20 years we're working on these things, but never have been asking for a project. This is like shooting balloon here and there and see why don't we try. Then once we come more closer to something at the end of the tunnel, then we went actually for a BMBF project, and this was a very successful one, and actually our new minister of BMBF, she is holding exactly the progress report of this project. The next one is the H2 on Air. In the H2 on Air project, we are utilizing actually very little containers for energy storage. There is a nanostructured powder inside, and that absorbs a lot of hydrogen, much more energetic-wise than batteries could do. The next one is the power to gas to fuel scenario, and to this scenario, if we have that time, we will achieve that to the end. Excuse me. Now, let me show you, okay, one more comment. I'm coming from Germany. I love my country very much. I'm a fan of Germany, but let me tell you, I'm also a fan of Europe. And this was not planned to be in this presentation here, but let me just remind you, as my colleague from Bayer this morning also mentioned, and I was very happy about that, we need to be a strong group in the future. And this strong group needs to be on this planet to be able to survive next to some other large groups that we're going to have. So I strongly believe in the need of Europe. That makes sense. So all what we are doing here with this almost already makes sense. Now, I'm representing actually a bunch of companies. Today, we are talking about the one on the very left and the second one to the right, which is Zoz Mobility, which is actually generating a marketing platform for hydrogen mobility. Very quickly, what we do. We are processing some equipment. With this equipment, so we are utilizing our own equipment, basically. With this equipment, we are making nanostructures. This here shows an HSS matrix with a superfine carbide distribution, 10 nanometers, just to remind you, 10 nanometers represents 1 nanometer, 4 copper atoms in a row. This is the distance we are talking about. And the grain size we are intentionally can create is in the range of 40, 50 nanometers, easily, and in large scale. Then with that, we are doing different type of products, and this including direct consumer ending product. And this I will show you. In Germany, this became quite popular because we are very much working into clean energy. Germany is the country for the energy turn, and we are talking about energy storage and sustainable technology. And this is called blue energy turn. Has nothing to do, and here again we are talking about IPCC, about the horror scenario of CO2 emission. For this, I really stand on the other side of the medal, and I tell you, I'm not saying I know everything better than IPCC, but I tell you, I admit that I don't know. And I believe that mankind, we are not aware of the correlation between CO2 emission or CO2 concentration in the atmosphere and the global warming, the global temperature. And for those who have other opinion, I mean, we name it Greenland. Greenland, Grönland. So it seems that there have been no ice anyway. And if the entire North Pole would melt away, the ocean wouldn't rise anything. It would go down and come back to the old situation. North Pole is swimming, by the way, just as a small thing. So now, energy turn in Germany. Energy turn in the entire world is absolutely correct and makes sense. But we are working on an energy turn since we came out of the jungle. We started burning what we have on hand, then we are going deep in the earth, then we are finding other technologies, we are jumping from one bridge to the other. And energy turn is perfectly right, but the question must be allowed. Is that the right timing? If this question is not allowed any longer, then we are doing something wrong. That is my opinion. So that has nothing to do with the fact that it's very good to try to save any kind of emission of mankind. We didn't do very much good things to this planet so far. And that means it's good to reduce emission, to reduce any kind of waste, etc., etc. Naturally, yes, absolutely. So, performance. With that, I want to show you what potential we do have in the future. The automotive device is probably the utmost technologically developed piece that mankind has in its hand. We go today for 200,000 kilometers. If this is 300,000 or 400,000, doesn't play a role in this moment. 25 kilometers on average, 8,000 hours in operation. Now let's have a look at us, the human being. The human being has a progress in years going up, 60 years. Gives us 525,000 hours in operation based on German data, on 2008 UBA-TREMO data, almost 1 million of transportation kilometers. And ladies and gentlemen, this on top is technology, this below that is evolution. And this gap in between is what we might reach one day with technology. And this is why technology is important, and this is why the future can and will be very bright. This is my understanding of things. Now, every day, sun and moon are giving us more energy possibility that we could utilize probably in the entire year. That is not a proven number, but that is probably not a wrong number. Now, we are only left with 3 questions. How to collect, how to store, how to transport this energy. And who will be able to answer these questions in an economic way? He will influence mankind's future for the next hundreds of years, definitely. For this, we need materials. Materials we don't have enough, not at all. We have planet Earth, Mother Earth, a few planets around it, and that's it. This is our fund. So if we have only this fund, what can we do if we need more? And for sure, we do need more. Only 2 chances. What we have, we must reuse. Before we come up with a product today, we must know, we must think about what to do after lifetime span, what to do in other applications, etc., etc. And the second thing, of course, is with the little we have, we need to generate more function, more application, so more use, and this is performance. Performance of material means less material for more application, and this is very naturally why we talked in past times, we talked about macro, meso, micro materials, and this is why today and tomorrow, this must be nano and nanostructure, definitely. Very easy thing. So, very quickly to the tantalum. What this is, we are controlling the grain size of this material, utilizing carbon nanotubes, and we had this representative from Bayer here this morning. We are actually ending up with an aluminium material that is as strong as steel, 700 megapascal, and this at half titanium cost. And the function and how we do it with SCIP, this is the bay tubes, how we started this project. Actually, that was a cooperation between Bayer and Zoz. And since Bayer stopped making CNTs, now we are doing it up by ourselves, just on our own note. Take care for your chair and for yourself. Jesus Christ. So, for the manufacturing capability, just to tell you, we are not talking about laboratory scale. We are talking about tons of material. This one gives you capability of 20 tons per year, and this one makes 100 tons per year in this material. After that, we go to a passivation step. That is something about nano safety, nano aerosol concentration has been observed. Then we go to consolidation by hot extrusion, and with this actually, then these kind of materials here, this is the semi-finished products that we have on the market. And this is them again. Now, just very quickly to the result here. Important thing, this is the specific strength of the material. For those who want to know the absolute strength, please multiply with the density. But of course, I want to show you that we are better than a titanium alloy. Titanium is much more heavy than aluminum. So this is why we go to specific one. And this is one of our targets here, where we now have also public funding or public-funded projects actually running on this topic, but now only to transfer it to other business areas. Now, coming to the cement, and this is this kind of bridge. We have started actually in cement, and this is a good reflection on the last session in so far. We have started 20 years ago with cement, never asking for a project. Shooting a balloon here and there. Here we are just refining ordinary Portland cement. What you can't see on this picture, this is simple optical microscopy. What you can't see is that we are refining also the grain size inside, and that we are activating the surface very much. We have been creating, in the last 2 decades, we have been creating materials with a compressive strength of a gigapascal. Ordinary material shows 50, 30, 40, 50 megapascal. This is 1,000 megapascal. So this is really different world, this is completely different material. So this material that we utilize here now shows in a glance a super high strength, shows extremely CO2 manufacturing, low manufacturing, and a super durability. I'm going to show you some of the glances here. The setting curve here gives you after 28 days, the ordinary material would end around here. This is where we after the first day. This is the CO2 emission saving potential, which is in the range of 20%. This is the actually mercury intrusion porosimetry, and that shows that after a few minutes processing time, we are moving from 50-50 capillary gale pores to 95 gale pores, 5 capillary pores. That means water cannot penetrate in this concrete any longer, which is an amazing result for durability of any kind of Autobahn bridge, any kind of building that is in water effect. Telling you something about dimension. This is one of my Chinese colleagues. Want to tell you he's not too tall. That means the plant here is also not too big. This is the unit that we utilize 2 weeks, 2-shift operation to make all the material for that bridge in Germany. So that is something that really can be done. The hard facts here, and the hard facts are only that, it's only that what counts at the end. We calculate the numbers, and we are ending up with this 7 here. This 7 is major importance, and this 7 means 1 ton of concrete will cost €7 more, is 3 times stronger than the conventional material, almost an endless durability, and saves a lot of CO2. Now, €7 per ton. Now let's see what the CO2 actually value is. We have €140 per ton total cost of that fraction that we use, and this gives us 395 kilogram of CO2 emission saving. That means here in this progress, we are paying every ton of CO2 emission, 1 ton of CO2 emission saving, we have to pay 350 euro. This assumes that our product would have a 0 value, but that is enough. I want to see if only the CO2 emission can pay for the entire product. And it can. It can. So the product actually is free in the end. And I went to German Automotive, and Dr. Ulrich Eichhorn, who is actually the managing director, he calculated for me this number here. And this number gives you the amount that German automobile industry in the future is expected to have their customers pay for every single ton of additionally CO2 emission saving. And this is twice the money that we actually utilize. What does that mean? That means practically that the politicians would need to go to automotive industry and tell them, please do not save any more CO2 before we have replaced all the ordinary Portland cement into other materials, into these advanced materials. So, the total number on this planet, in Germany, we could save actually 0.6, on the world 0.5% of the total, of everything, of the total CO2 emission, which is really a huge number. We came up with a second demonstrator. This was set up in Germany in 2 months, 3 months, 4 months ago. And we are looking at more bridges. Actually, this is my hometown. And within this year, we hope to finalize this bridge here, and then another one over there will come. So very quickly to hydrogen storage. This is the little tanks. Could you give me 3 more minutes? Thank you. So, new topic now, okay? So this is hydrogen storage. This is how can we ride our car in the future? What does that? That has to do with concrete. Basically nothing. But the system, the principle, the technology we are utilizing is almost exactly the same. And this is a tank, and in this tank there is some powder. And we came up, you know, since 15 years we make so-called solid-state hydrogen storage materials. This is metal hydride systems. And within 15 years, automotive didn't really succeed with that. And so then we stopped with that a few years ago, and I said to my colleagues, either we stop it at all, or we have to make a tank. And then you make a tank, you bring your powder in that, and then you realize where the market could need a tank. So you have to make a vehicle. And then if you have a vehicle, you have to find your customers. So this is the way how we are trying to follow that. And then we started with very small-scale vehicles, and like this vehicle here has actually a range of 120 kilometers. This is a kickboard, right? But with 2 1-liter containers, refueling actually €2. And so from there, then we go and say, okay, let's calculate a car here. And for this car, we actually calculate the 300-kilometer range, 75 kilowatt hours. For this, we would need such kind of tank, or we would need 23 of these 1-liter units. Now, everybody would smile and think, 23 tanks in one vehicle? I tell you, go to the gas station, make 23 times, clack, 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 clack. You are faster than today going to the gas station with your gasoline-consuming car. Now, then this is something for the gas meter, which is a very nice patent on that. This is something about the fuel cell. That is the next problem, because we need affordable fuel cells. And for this reason, we are also deeply in this matter. And what we claim here is that we might see that we are suggesting a potential revolution in the refueling infrastructure. In the future, you could refuel your car in any home depot, where we have already such kind of little containers just for the soda machine in your kitchen. In the future, you might go to a vending machine, like where you go and get a Diet Coke today. You throw the old can, put €1, get the fresh can. And that could be the way. And one important thing here is, with these metal hydride, with the hydrogen storage materials, today, we are a little better than high-pressure gas. We are better than the battery. We are much worse than gasoline, of course. But the reason why we decide for the metal hydrides is the potential that is there, that is given in the future. For high-pressure gas, we have gas constant, and we have upper left table situation in the periodic system of the hydrogen. This Bore4Store project here, this is one of the, in the FP7 program, we are working on metal hydride, on complex hydride systems beyond 10 to 15% of weight capability in hydrogen storage. If then with 3-4 cans we could ride our car 300 kilometers, then this thing is going to become real funny. So the H2 on air, this is a little aircraft, and I will skip this topic, and then I'm coming to 2 more pictures only. This actually can be, you could read that in the ERDS bulletin. This is the second, the third last one. And here we are equipping a car, and here we are also equipping an aircraft with these little bottles and with a kind of range extender function with a fuel cell, actually. Now, and this car here, this will go with a few of these containers. We are doubling the range, and it's exactly the same platform that we are developing at Airbus ERDS for the aircraft. Now, that was this refueling infrastructure. Now, finally, we would have to look into power generation. This is the last picture. It doesn't make sense to do it without it, because from here to here, hydrogen, to bring it on your wheel, is energetic-wise a fiasco. A combustion engine is also a fiasco, but this fiasco is even bigger. So there is only one chance to really realize that. And this chance says we must come into the position not to consider energetic efficiency. We must have a position where we only need to consider economic efficiency. If this is given, everything is fine. And that means there's only one chance. It cannot play a role how much hydrogen we are losing on the way. So that means hydrogen must be generated renewable. Only then this thing can make sense. Otherwise, we could forget about it. So ultimately, we need renewable energies for this kind of principle. On the opposite, on the contrary, this would give us an amazing, a fantastic energy storage, which is the big lack of the renewables. So we are calculating always 4/5 of wind, 1/5 of solar. Why is this? Energetic-wise, wind is much better than solar. However, wind, we have 2 weeks zero wind, but we don't have 2 weeks zero daylight. So if we bring in a portion of solar, then deviation goes down, and that means my tank can be smaller. So, and then from there, we must go to the wheel. And one last sentence to this. Power to gas economically has a problem against power to gas to fuel. If you take renewable electricity and contribute this to electricity, you get a contribution of A. If you take the same renewable electricity and contribute that to fossil fuel, your contribution is X times A, because the energy content that you pay at the gas station is much more expensive than you pay on the socket. So that means this is why we should go to power to gas to fuel. Okay, last picture. Everybody is very much invited, if you want to hear more about these things, to the next international symposium on nanostructures. This is always alternating every year, Germany, Japan, and next time is in March in Germany. And I would be very happy to welcome everybody right there. Thank you very much.